for this session, get the speakers all put into the panel. And Matt, I'll just go ahead, since I see you're able to speak already, I'll go ahead and pass it off to you to introduce the session because it was a session that you had developed.
Thanks, Lisa, and all, and thanks for folks tuning in or staying tuned for the end of the day. So we organized this session to talk about different modernization efforts for survey data analysis. So we're excited to present these different thoughts and ideas across a few different projects. I'm going to kick off the first presentation, then quickly hand it over to my colleague Marcia. And each presentation will be about 15 minutes. I'm going to put a timer on here. And just a reminder for people either joining or have been here all day, feel free to put things in the Q&A. So let me see if I can share my screen here. All right, can you all see this? All right, I'll take that as yes. No one's screaming at me. Okay, so I'll kick it off here. Um, this first presentation, we're going to be talking about data estimation and dissemination pipeline. So I'm going to talk for just a couple minutes and I'll hand it over to Marcia. So first talk about small area estimation. So lots of people are familiar with this, but the idea is we collect data for a specific purpose at the national or regional level, and we want to answer questions that weren't originally designed to answer. For example, state and local granular estimates. So what do? We try to use statistical models and auxiliary data. One of the ways we do that is through small area estimation models. They combine sort of direct estimates from the survey data collection and predictions from a regression model. And they kind of do this smoothing or borrowing strength across domains. So the idea here is, well, if we have a national level data set, can we produce state level estimates using these models? And one of the constraints we have is we don't want to do a customized modeling approach for every outcome. We sort of want to do a general purpose approach. So this is sort of our workflow where we identify auxiliary data. Hopefully it's easy to get through an API or through some other partnering. Um, and we pre-process that. Then we look at the data from the direct survey data collection. We generate summary statistics. We put those into a model to train, and then we validate it. In terms of the implementation that we've been working on, we want to use off-the-shelf software, and we want it to be able to run a variety of environments, restricted, desktop, cloud. So we looked into some packages in R that run Stan, in particular TIP SAE, which runs small area estimation models in Stan. And we're currently developing a methods manuscript and a GitHub repo that will be released at the end of the summer. So I wish I had a link, but we'll follow up on that. Typically, the results we see, we look at the variance and the standard errors. Sorry, we look at the point estimates and the standard errors. For point estimates, what we see is the direct estimates on the x-axis are what's coming out of just from the survey. On the y-axis are what's coming out of the model. And we see for larger sample sizes, larger domains, they match. And for smaller domains, they don't. They tend to get shrunk towards the mean. And that's typically what we want. It's a more stable estimate. When we look at the variances, the direct estimates from the data collection are almost always larger variance than the model-based ones. And again, that's the intent, is to have more precise estimates. So that's a quick intro to model-based estimates and why we're doing it. And then I will pass it over to Marcia.
Hi, good afternoon. And I'm here to talk about our dissemination aspect of the model-based estimate work.
Marcia, do you need me to share? Or are you going to share? Sorry.
Oh, I'm trying to share. Are you able to hear me?
I can hear you.
Second. Screen sharing. One moment.
All right, I can see your screen.
Okay, great. So I'm Marcia Underwood. I'm with the Center for Data Science, also at RTI International, and I'm going to talk a little bit about the dissemination aspect of the work for this project. Once we had these model-based estimates, we wanted a good way to be able to understand and interpret them. So the dissemination project process on this really fell into three main sections. And the first of that was getting to understand the data, understand the client requirements, and figure out our data structuring, those kinds of concerns. Then we moved on to some exploration of various solutions for visualizations, figuring out which comparisons and filters we wanted to use, those kinds of questions. And then we moved on to our final phase of this, which was iterative development. And we did resolve to make a interactive web application for this, which is a custom JavaScript-based application. So in getting to know the problems here, there were two main considerations that we found once we started to get familiar with this. The first of those was with these being model-based estimates, making sure that we were communicating the uncertainty around those estimates was going to be a big part of the communication goals for this project. And another thing was size, with them being small area. In one of the two data sets that we were working with for this work, we were dealing with things at the county level with quarterly data for several years and multiple demographics. So both in terms of number of rows and in combinations and permutations for building an interactive dashboard, there was a lot to work with there. So this is what we narrowed ourselves down to in kind of some of the priority goals for the tool, about having a good user experience and an engaging presentation, and then filling requirements such as accessibility standards and the ability for the tool to be updated without any need for development work for regular updates. And then as we moved into the exploratory work, a lot of the questions are, true of many kind of interactive tools and visualization solutions about really needing to make decisions on how much data to include and what kind of comparisons could be made, because tools that overwhelm users just generally don't get used at all. And so we, especially with the tool where we were hoping for this to be used by the general public, we decided we needed to really prioritize a few main most useful comparisons and limit some of those options. So here we have example of two visualizations that we actually did not make the final cut, just to kind of give an example of the process. I did most of my exploration work here in Tableau, even though we did a custom application for the final tool. Tableau allowed us to kind of try out the ideas more quickly along the way. So an example here, we're like ranking each county for a particular demographic group. We tried some options actually mapping a change over time, but in our final solution, we ended up with three main comparisons. We start off with an initial view. So we're having kind of a macro to micro approach here, initial view with a geographic comparison. And then once the user selects a specific location, it's only then that we allow the demographic breakdowns and those more granular views. The web application itself was created using Harness View, which is a plugin that was developed actually within Center for Data Science, championed by my colleague Alex Harding, and it controls a lot of state management and dependent filtering, those kinds of things for making dashboards for the web. So that's kind of an organization and time-saving helper for us. I'll talk a little bit about the application itself and the visualizations. So here we have just an example of harness in use of the tool itself. So the data for this tool was stored and it's web accessible on an API. So we're able to query that data and only get the data that we need for any particular view that a user is looking at one time. Here's an example here of getting the distinct values for a particular data column and then being able to set the dependent actual drop-down menu filter options within the tool based on those retrieved dependent values. One nice thing we were able to do in building this is actually use one single code repository for two different data systems. And then we're able to create a final built deployable version based on those environments. But that enabled us to share a lot of the filtering logic, but not all of the visualizations, a lot of our formatting decisions and other concerns. And some advantages of making custom visualizations were just a lot of fine control over the visualization, such as layering a lot of information onto a single visual, such as confidence intervals, reference lines, flagging for unreliable estimates or suppression, being able to have a good control over our range to domain pairing for scales, and a lot of control over labeling and interactivity. So as I mentioned, with these, showing uncertainty was really important to the tool. So an example of this here on the maps themselves, anytime one mouse is over a county, my solution here was to add a secondary instance of the full map scale into the tooltip. And then that confidence interval is visible and the point estimate right on that scale every time you mouse over a specific county that updates. And the same is true for state level view for one of the other data sets. And confidence intervals can be kind of difficult on multi-line charts. They tend to overlap a lot. And so our solution here is that on hover, either over the line itself or over the entry in the legend, you're able to see that confidence interval there. For our map scaling, we're able to kind of have control over that. So an example here, you can see we have a scale looking at a particular cause of death here. And the maximum on the scale at the national level here is 107, but we're able to, reset that scale looking at this in the context of a selected state. So at this particular, for Illinois here, we have a scale of maximum of 37. Anytime we do allow those demographic breakdowns, we included reference lines on all of the visualizations. So you can see a reference line here for an all value when we're breaking down by age on the line chart and represented by the vertical line on our single year view. We also had a lot of control over missing values on trend lines, which can be sometimes an issue depending on the tool you're using. And also with doing something custom here for accessibility, we have labeling on every single data point that's shown within the tool. An example of some additional interactivity we're able to allow here. Once you are looking at a single year or a single location view here, if you're able to select a demographic, we allow two different options for the major or minor grouping here. So in this case, you can look at something either by a secondary demographic breakdown here, or since we're looking at these specific health topics and they have a variety of different outcomes, we also allow toggle ability here to actually compare out those individual outcomes for that demographic. So that's the kind of interactivity that we had an advantage of in doing a custom application. And then in finalizing our work, we did rounds of review with our subject matter experts and refined based on their feedback. testing for various browsers, 508 accessibility testing, and security scanning, and within our client environment. Thanks for letting me share a little bit of our work with you today.
Thanks, Marcia. Again, if you have questions, please put them in the Q&A. Our next presenter will be Victoria Scott. She'll be talking about integrating Sudan into modern analysis pipelines. Victoria?
Hello. Let me get sharing. This one. All right, can everyone see my screen?
Yep, can see you, can hear you. It's all yours.
Great. So my name's Victoria Scott, and I'm also with RTI International, and I'm going to be talking to you today about Python callable Sudan. All right. So if you're not familiar with Sudan, it's a tool for conducting statistical analyses, and it allows you to specify your survey design. So that is your weights and stratification and clustering, so that you can correctly calculate your variances and your standard errors. Most of our Sudan customers use SAS callable Sudan, and there is a standalone version of Sudan, but it's not really designed for data manipulation. So for customers moving away from SAS, RTI has developed a version of Sudan that you can call from within a Python environment, and that is what I'm going to demo for you today. So there are two ways to access Sudan from Python. You can access it interactively or in batch. So the first example here is submitting it interactively. You would import your procedure, or sorry, import your the Sudan package, and then you would use this function, Sudan_proc, and what you pass to this function is the list of pandas data frames that you're going to use in your analysis. And then once you submit that, you'll end up in this Sudan prompt here, and now you can type in Sudan code. And that, if you're familiar with Sudan code, that Sudan code would look pretty much exactly the same as Sudan code that you're using now. And then when you're ready to run it, you type run. And then when you're finished, you type exit, and then you're back into your Python environment with access to the output data. So let's see what that looks like in real life. Okay, can you all see the command prompt?
Yes, thanks.
Okay, good. So I'm going to open up Python, and I have this. Let me find it, sorry. This is my Sudan code that I want to run. So Sudan code looks a lot like SAS code, and I'm going to pull in these data sets, Boric, DARE, and EPIL. And I'm telling Sudan that they are pandas data frames when it's pulling them in. So I'm going to start off by, because I'm working with pandas data frames, I'm going to import pandas, and then I'm going to import Sudan. Okay, and then I'm going to pull in my data sets, which happen to be SAS data sets. So I'm going to pull those in and convert them to pandas data frames. Okay, so I have these 3 pandas data frames that exist in my session right now. And I'm going to open up an interactive session with Sudan. So I have my call proc.sudan_proc. And here I have the names of my pandas data frames. So on the left-hand side of this equal sign is the name that is in my Sudan code. And on the right-hand side is the name of the pandas data frame. When I'm working with this, I generally just make them the same because it's easier, but they don't have to be. So if we can see, my EPIL is EPIL, but I can pass the pandas data frame 1 as that data set. So now when I submit that, I have my Sudan code, and now I can just copy paste my Sudan code in. Right, so Sudan is not going to submit this. It's not going to do any of the analysis until I type run. And now it's done my analysis, and it's gotten my output. This is all my output here. And you can see I have a warning, but that is something that we're not going to worry about right now. All right, so if I have more Sudan code that I want to submit, I can just do that. So I'm just going to do all of this at once. You don't have to do it. You can do it line by line if you want. You can do it, well, you can't submit it line by line, but you can type it in line by line, or you can put a big chunk of code in and then run, and it runs all of it. And then when I'm finished, I just type exit, and I'm back in Python. So what is returned from this Sudan underscore proc is a data dictionary holding all of my output data sets. So I requested 3 output data sets in these. Example 2_1, 2_2, and 2_3. So if I want to get to those, I saved all of those in result in my initial call. So if I want to look at result, and I can see the keys of that data dictionary there, that's them there. And if I want to actually use one of those data frames, I can just refer to it like this. No, that's right. So that's my output data set. All right. So that is what interactive Sudan code in Python looks like. So that's all well and good if you're developing all your Sudan code, but normally if you're processing a lot of data, you're going to want to have it to be able to batch submit it. But in that case, you can't use Sudan underscore proc because, and then just, paste your Sudan code below it, because Sudan code, as you saw, does not follow Python syntax. So you'll have to save it in a separate file and use this second function, Sudan underscore batch. And this works almost exactly the same as the first one, the Sudan underscore proc. It's just the only difference is that the first argument you have to give it is the path to your batch file that's holding your Sudan code. But then you also pass it the pandas data frames that you're using in your code. So I'm going to show you an example of this, but before I do that, I'm going to talk about some options that are available in both the batch and the interactive functions. So the first option is the screen on or off. You see the output is long. It's really, really big, and you might not want that and to display, and so you can turn it off. And then the second the second option is output. So if you turn your screen off, you still probably need to see the output. So you can tell it where you want that output to go. By default, it'll save it as output.txt in your Sudan working directory. So when you install Sudan, and when the first time you use Sudan within your Python environment, it will ask you for a working directory. This is just where you want it to save temporary files that Sudan's going to use while it's running. And so you specify that the very first time you use it, and then that's what it's going to use as default. But if you don't want it to go to that default, you can specify something else. So let's see what that looks like. All right. So if I'm going to run this in batch, and I'm going to use my options. So I have my Sudan code saved in example.sud. You can see that's the same code that I submitted before is saved in example.sud. And then I'm turning the screen off and I'm sending my output to example.txt in this same folder that it's saved in. And here I'm still submitting the names of my pandas data frames. And so now when I run it, it doesn't show me all of that output. It just tells me that it's running. And then when it's finished running, I'm back. I have my prompt for Python. And this one I saved as result2. So I can still see result2.keys. I have my my data dictionary saved in result2. And if I want to see my output, I can just see example.txt. And here it is. All right, so the next question you might have, or a question you might have, is, do you have to use pandas data frames? And no, you don't. With this Python callable Sudan, you can use, you can submit pandas data frames, but you can also submit CSV files, Sudan files, Sud export, ASCII, and SAS export files. And the only ones that you actually have to pass into, like, through the function call are the pandas data frames. So if your Sudan code, for example, looked like this, you have a CSV file type, then here you would, put your path to your something like that. And you would just without CSV. There. So you would just give it the path to your data set. And so that you would do the same thing if you had a Sudan or other data type. And your output can also be either pandas data frames or any of these file types. So that is all I have, unless anyone has any questions.
Thanks, Victoria. Yeah, just as a reminder, put your questions in the Q&A, and also if there's anyone else on the panel has questions, you can also jump in with ones. Hopefully we'll have some time at the end of the session if people are taking a minute to formulate a question. So thanks, Victoria.
Yeah, you're welcome. And if you do think of questions, or if you want to try this out, please contact the RTI Sudan office at sudan@rti.org.
Okay, next presentation will be Hunter McGuire, and topic will be challenges in multi-level modeling and uncertainty estimation for survey data. Hunter?
Okay, do you see the slides?
Yep, see it, we hear you.
Okay, awesome, thank you. So good afternoon, everyone. My name is Hunter McGuire, and I'm a researcher in epidemiology and biostatistics at RTI International. And so today I'll be talking about some of the key challenges we face when applying multi-level models to complex sample survey data, particularly when it comes to estimating variance and uncertainty. So just to give a brief background, complex sample surveys often use design features like clustering, stratification, and weighting to make sure the samples represent the population. But these features also introduce complications for analysis, especially for hierarchical and multi-level models that weren't formulated with the survey design in mind. So in this talk, I will cover some of the initial investigations that Matt, I, and others have been conducting on how we can better estimate fixed and random effects from multi-level models when they come from a complex sample survey. And also to manage some expectations. This is certainly a work in progress, but I think we have some interesting results so far in our work. So just to give you an idea of the agenda, so I'll go over with a motivating example that Matt and I encountered in our work, where we tried to apply multi-level models to complex sample survey data. And through that, I'll provide a background on complex sample surveys and multi-level modeling in general. Then I'll describe the simulation study, the methods that we use, as well as the results that we had in take-home message, and then some areas for future research in this area. So first, just getting into the motivation. I wanted to first start with a brief overview of how multi-level analysis is structured and what information it can give us so that we're all on the same page. So often in research settings, we have nested data such as residents within neighborhoods or students within classrooms. And this nesting or clustering can often hold relevant information for the design and implementation of interventions and also estimating the variance of our outcomes. So for example, we can ask whether health outcomes such as blood pressure are clustered within neighborhoods. And if so, what is the reason for that clustering? So this approach can also allow us to investigate some of those upstream social factors and how they may influence patterns of health and disease. We can also separate the differences we observe into those between the neighborhood averages versus the variation within each neighborhood. And then we can also visualize this information using the figure to the right, which shows blood pressure values clustered by neighborhoods within a city. And you'll see that the blue line that I just highlighted represents that citywide average. But you'll also see with the orange lines that blood pressure measures are also clustered within neighborhoods, with some neighborhoods having a higher average blood pressure and some neighborhoods have a lower average blood pressure. And so while researchers often use multi-level modeling defined by either geographic or administrative boundaries, Claire Evans and Wanda Merlot proposed a multi-level approach to investigate health disparities and inequities between social groups. So instead of actually nesting people within neighborhoods or schools, individuals are nested within their socially defined intersectional groups or positions. And these are used as proxy measures for systems of oppression like racism, sexism, and heterosexism. And so using this approach, we can estimate whether health outcomes are clustered within these intersectional positions, similar to how we would estimate it for neighborhoods or for schools or classrooms. We can obtain the direct estimates of the risk or prevalence of a health issue for an intersection. And then we can also evaluate whether the main effects or the average associations describe the disparities or inequities we see, or if there's a more complex interaction effect that place certain groups at increased or decreased risk. And so really a key function of this modeling approach is variance decomposition. So we need to have accurate measures of the random effects to generate stable estimates for the prevalence or the risk of an outcome for an intersectional group, or whatever the application of the multi-level model is. However, as I talk about on the next slide, estimating variance of random effects becomes tricky for multi-level models when we have complex sample survey data. So there are a few key ways in which variance estimation is complicated by having complex sample survey data, especially when we want to use multi-level models. So first is that the design features of the survey often violate the assumption of the observations being independent and identically distributed, or IID. And that's a key assumption of standard multi-level modeling. Also, multi-level models such as students within classrooms or patients within hospitals assume some hierarchical structure to the data. So the complex sample survey can introduce non-nested, cross-classified, and informative cluster sizes, making it difficult to separate that within group and between group variance. Also, estimating the variance components themselves, such as the variability between intersectional groups or between neighborhoods, is already challenging, but when the data are weighted and clustered, estimates of these variance components can become unstable and biased without specialized techniques to handle the survey design features. Also, most of the standard multi-level modeling packages like LME4 and R, Proc Mixed and SAS, they do not natively account for complex sample survey designs. And conversely, on the survey analysis side, tools like the survey package in R or the survey functions in SAS are often limited in handling multi-level random effects. So, and then finally, if the probability of inclusion is related to the outcome of or the random effects, ignoring the design features can bias estimates to make variance estimation inconsistent. And so these are just a few different ways that we run into issues when we try to estimate variance in multi-level models with complex sample survey data. And so on this slide, I'm outlining our approach. This is the first phase of our investigation into addressing these challenges with variance estimation and multi-level models. So first, we're going to examine 3 different variance adjustment procedures that Matt has been working on that could help account for these complexities of the survey design. And I'll describe these in more detail later, but briefly right now, there's the naive adjustment, the prior curvature approach, and then the Yale-Johnson power transformation approach. And then next, we implemented a simulation study to see how each of these procedures affects 2 key outcomes. One was the credible interval width, so which here we define as the difference between the upper and lower bounds of a Bayesian posterior interval. And then the coverage, or the percentage of times that the true population parameter fell within that 95% credible interval across all of the simulated data sets and models. And this setup allows us to compare the methods in terms of both precision and accuracy, with the goal of identifying an approach that balances both in the context of complex sample survey data. So now I'll get into the methods that we use. First, talking about our simulated data. So we generated a population data frame with a 1-stage cluster design in this initial approach. Our total population here had 10,000 individuals. And then also to simulate that group assignment. So this could be seen as like the neighborhoods example or the intersectional group example. We created 30 groups with varying sizes to mimic those real world sample size imbalances between groups at level 2 in a multi-level model. And then in terms of data generation, we used these parameter values for our fixed and random effects. So we had 2 fixed effects. One was just a simple intercept, which we set at -2, a fixed slope at 1. We had 1 level 1 predictor and random effects. So each group that we had up there, so there's 30 random intercepts here for the grouping level variable. Then we had a latent linear predictor, mu, that was predicted by the intercept and the fixed slope and level 1 predictor, and then the random effects. And then here we had a binary outcome, so we just did the inverse logit of the mu with the Bernoulli distribution. Getting into the clustering aspect, so we had 1,000 clusters of 10 individuals each, so there's equally sized clusters in this population to get to our 10,000 population total at the individual level. Our sampling scheme we used was probability proportional to size, or PPS cluster sampling. So these PPS probabilities were based on the mean mu value within each cluster. And so clusters with higher mean mu values had greater probability of selection into our samples. And then we undertook a sampling process where we selected for each sample 100 clusters. This equates to 1,000 individuals, selected via that PPS sampling approach. And then all individuals within the cluster were selected. So there was only 1 stage of selection. And then the outcome here is that we have now 100 independent samples that were drawn from that full population data frame that we described earlier through that data generating process. We also use Bayesian methods here, and I just wanted to go over just a brief background on some of the differences between the traditional frequentist approach and Bayesian approach. So in the frequentist paradigm, parameters are typically seen as fixed and data are random, whereas Bayesian paradigm data are fixed and parameters are random. In frequentist, where you're asking the question, what fixed value of theta is most likely to have given rise to this data? And in Bayesian, we're saying, given I have observed the data, what do I know about the possible values of theta? For inference, so inference is based on the sampling distribution and repeating sampling in the frequentist. And then in the Bayesian paradigm, inference is based on the posterior distribution that we derive from our models. So there's another key difference here, which is the interval definition. So in frequentist terms, we use confidence intervals. So for example, a 95% confidence interval means that if we perform a similar procedure many times, theta, our estimated value would lie, our population value would lie within the 95% CI, 95% of the time. For credible intervals, it's more simple. It's just that a 95% credible interval means that theta lies in the interval with a 95% probability given our model and our data. Frequentist paradigm also usually relies on p-values. So the p-value is just the probability of obtaining a result as extreme as the observed data, assuming the null hypothesis is true. Whereas in Bayesian thinking, we're thinking about the posterior probability, which is the probability of the hypothesis given the prior beliefs and the observed data. And so as part of addressing the uncertainty in multi-level models with complex sample survey data, we explored 3 approaches to variance adjustment. So each method modifies the MCMC samples or the Markov chain Monte Carlo samples to better reflect design-based uncertainty. So I'm going to walk through each of these briefly, and I've highlighted in bold where each one primarily differs from the other approaches. So the first one on the screen is the naive adjustment. So this method just uses the unconstrained samples, posterior samples as is without any transformation. We then estimate 2 key matrices, the H matrix, which captures the model-based curvature of the posterior, and the J matrix, which represents the design-based variance. We then apply an adjustment matrix using a sandwich variance correction. So it rescales and rotates the sample draws to account for the mismatch between H and J matrices. And then finally, we transform those samples back to the original parameter space. Next is the prior curvature method. So like the naive method, it also starts with the raw unconstrained posterior samples. And here again, we estimate H and J, but with one key difference. That's that we incorporate prior curvature. Specifically, it adds the curvature from the prior distribution into the adjustment. So instead of just producing or just using the model-based curvature, we estimate the Fisher information as J plus H naught, where H naught comes from the prior. And then the prior informed adjustment matrix is then applied, and then the samples are transformed back to their original scale like the naive adjustment. And then lastly, we have the YJ power transformation. So this method starts off differently than the others. It applies a Yale-Johnson power transformation to the posterior samples. And this helps stabilize the variance estimates, especially in cases where normality assumptions don't hold well. And then instead of estimating the H matrix using curvature, we estimate it using the inverse of the posterior variance of the posterior draws. And then similar to before, we apply the adjustment matrix using the H and J mismatch, and then transform those adjusted samples back to the original parameter space. So in summary, all 3 methods share the same general goal, which is just correcting for the discrepancy between model-based and design-based uncertainty, but they differ in how they estimate curvature and whether transformations are applied to the samples upfront. And then finally, I also want to shout out the CS sampling package, which is something that Matt has been critical in developing, which is a way to analyze complex sample survey data using Bayesian methods that we're outlining here. So this allows for Bayesian estimation of models using data from complex sample surveys. You can quickly build models with BRMS syntax, which allows for survey weights. And it also uses the Lumley survey package features to generate replicate weights and produce a variance adjustment weighted to a weighted posterior with BRMS and STAM. So now I'll just get briefly into the results that we have so far. So in terms of the credible interval widths, here on the screen, I'm showing the average value for the fixed effects, which are those 2, beta 0, beta 1, and then the average value for the random effects, which are those 30 random intercepts for those groups. For here, we also compared to an unadjusted model. So this is one where there was no adjustment that was taking place. You see that, for example, on the fixed effect side, that the posterior intervals are quite similar between the unadjusted model, the naive adjustment, and the YJ power transformation. But then the prior curvature induces a wider interval of uncertainty for the fixed effects. On the random effect side, the posterior intervals are generally larger for the unadjusted model, and they're much, much smaller for the naive adjustment, and then slightly smaller for the prior curvature. And then the YJ power transformation, they're a little bit larger. And this will all make a little bit more sense in the next slide, where we get to the actual coverage of the population parameter in these credible intervals and why this interval width matters.
Just about another minute, Hunter.
Okay, yep, got one more. So just to look briefly at this, the unadjusted model covered actually the population parameters very well in this example. So 93% coverage of fixed effects, 96% for the random effects. But then we look at the naive adjustment, it does poorly for the random effects at 47%. Prior curvature does a little bit better, 87% coverage, and the YJ power transformation does the best at 97%. So just some key takeaways and areas for future study. So the key takeaways here, the fixed effects are actually consistently covered by all those model specifications, but compared to the naive adjustment, the YJ power transformation performed best in terms of interval width and interval coverage of the population parameters for the random effects. So this is 97% coverage versus 47% coverage, which is a pretty huge difference. We also noticed that the unadjusted models in this case, where we just used a single cluster design or a single stage cluster design, did not have serious coverage issues. So in the future, we just want to explore some more changes to the survey design that maybe could induce some changes there. So thinking about unequal cluster sizes, adding in more stages of selection, and then making the selection probabilities dependent on the outcome or predictors. And that's all. Thank you all so much.
Thanks, Hunter. We do have a question. It might make sense to respond to type it up, but just want to direct your attention to the question.
Okay. Thank you.
Next up is Taylor Lewis, who'll be talking about combining probability and non-probability data. Taylor.
All right, thank you, Matt. Want to see my screen? Full size, I'm assuming.
Yep, we can see you.
All right, so this is a talk based on a broader project where we were working with a client in a nationally representative health survey scenario where we were trying to consider methods to possibly bring in, by means of a non-probability sampling and data collection approach, additional cases. And so we looked at various methods of identifying those cases outside of the traditional probability sampling scheme, and how we would put things back together into forming a single set of estimates using data from both the probability and non-probability sample data. So I'm talking about an excerpt of that analysis today, and I'll give a shout out to my collaborator, Mahmoud El-Kasabi, who couldn't be here today. So I'll be giving this talk. So again, the background scenario we have here is that there's a nationally representative survey. Estimates may be desired for individuals in a rare population domain. It could be one of a variety of domains, for instance, American Indians, Alaskan Natives, individuals living with HIV or AIDS, or children under 2 years old. And under a traditional probability sampling approach, there's a great likelihood that you just don't have enough cases within that domain to generate point estimates with sufficient precision. There would be insufficiently precise estimates. So there are some techniques you can use to come up with additional sampling frames to try and get more of those cases. You could also consider, as many organizations are starting to do, non-probability sampling approaches. So venue-based sampling, referral sampling, commercial panels, those are all techniques of non-probability sampling, or at least quasi-probability sampling that we see more and more these days. So one thing that was unique about our estimation goal is that we wanted to generate estimates for individuals in a particular domain, and we wanted to use data from both a probability sample, that's sample A, and a non-probability sample, sample B. And we're assuming in our scenario that both samples have the key outcome variables as well as demographics and covariates. It's just that there's no weights in the non-probability sample. So sometimes there's a scenario where you have a probability survey that has the X's and the Y's, and a non-probability survey or sample has just the X's, and so you do some modeling to kind of fill those in. But as you can see in this visualization, our scenario was that we actually did have both the Y's and the X's and weights that should be reflective of the larger population in sample A. It's just that we're missing those weights for sample B. So we want to create a combined data set with records from both samples, and both of those samples having representative weights that can be used to generate estimates and combine them into a single estimate. So the first stage in coming up with this combined estimator would be using the non-probability sample to generate an estimate, a population level estimate. So starting with a series of weights of 1, the goal would be to create pseudo weights from that non-probability sample. And there's a couple ways of doing this. There's actually more than just a couple. There's a lot of varieties that are closely related, but just to throw out a couple examples, and then we'll see some R syntax with the non-prob SVY package momentarily. One method could be, well, we'll call this propensity score adjustment. Let's assume that the probability sample is representative of the target population and estimate the probability of inclusion using those shared covariates. Okay, so it's basically like saying the non-probability survey may have covariate imbalances. If we can assume that those are related to the outcomes we're interested in, let's anchor our non-probability data to that probability survey and generate these propensity weights, which, well, the propensities are the estimated probabilities of being selected into the non-probability design, which could then be used to create pseudo weights that rebalance the non-probability sample so that it looks more like the probability sample. So this is using propensity scores that are used for non-response adjustment in surveys and a whole lot of other reasons to generate survey weights to make that non-probability sample look more like the probability sample. Another example method that you could use is calibration weighting. So the idea here is to identify a series of covariates. This may come from census data, administrative data, some other source that's external to your data systems, and assuming that those covariates map to covariates you have in your non-probability sample. The idea here would be to assign weights in your non-probability sample such that weighted totals by, things like age categories, race and ethnicity categories, match to those benchmark totals. So we start with the weight of 1, calibrate the weight so that the totals match for various demographics and demographic categories, these calibration benchmarks, and then assume that the non-probability sample has been properly adjusted for to look more like the probability sample, and then things can be combined in a single estimate derived. So just to show an illustration of method 1, a handy tool that's out there is the non-prob function within the non-prob SVY package in R. It has a dependency with the survey package. You can see it ends in SVY. And what the survey package, if anyone uses that for complex survey data analysis, one of the precursors to actually conducting your analysis is to create a design object that houses information about the probability sample. So this is where you would identify things like whether there's cluster variable, whether there's a stratification variable, whether there's weights. So that's the first thing we need to do. And notice how that's being done for sample A, which is the probability sample. But then we can use the non-prob function within the non-prob SVY package to generate propensity score adjusted weights. So that function, notice how the data equals is pointing to sample B, your non-probability data set, but we're still pointing to the survey underscore design object. And the two other things to point out is that we would have a selection clause where we'd identify variables. These would be the covariates that you would have in both sample B and sample A that you would want R to generate the estimated propensities and thus the propensity score adjusted weights. I'm doing that here with the logit function. Other choices are probit and complementary log-log. But executing this will generate on the est underscore PSA the weights variables, which will be the propensity score adjusted thing. So there's a lot going on behind the scenes. Again, it'll link back to the probability sample using the covariates in your selection clause. It'll generate these propensity score adjusted weights, which may need to be scaled. All right, if you're estimating a mean, it's probably not a problem. If you're estimating a total, you may want to scale them up or consider what the scale of those is. Okay, so speaking of scaling, one method that goes one step further, okay, the example method 2, the calibration approach, it still uses, in this syntax here, we're still using the non-prob function within the non-prob SVY package. But here the syntax is a little simpler because we're only specifying population totals that we want the weights to sum to. So in this instance here, I have 3 example covariates. They're all dichotomous. The intercept has the population total that I want the weights to sum to. And then these 3 values below are for the dichotomous covariate, what we want the total to sum to. So things are a little simpler here. It's going to start with the implied weight of 1 and inflate the weights for these covariates in the sample overall such that it matches this vector of population totals. And that'll also be stored in the weights object within est underscore cal. Okay, but the benefit here is that we have weights that are now rescaled to some known population totals. There's a lot of different varieties within the non-prob function. I recommend you check it out. There's some versions that can do both the logistic regression propensity score adjusted technique followed by this calibration adjusted approach. I'm just showing a couple methods that are relatively simple just to give you a flavor of the kinds of things that are available in this off-the-shelf package. Okay, so once we have the 2 data sets, sample A, which is, we didn't really need to do too much to it. We're assuming it has cases in the domain of interest with weights that sum up to our best guess of how many cases in the population there should be for that domain. And now we have sample B with these weights that have been adjusted, let's say, through the calibration approach. So we have 2 data sets effectively that have weighted totals that are in and of themselves estimates of, say, some total. So that's y hat. If we want to combine them, one way to do that would be to use this composite estimation approach. So basically assign a term alpha, something between 0 and 1, to give, some portion of weight to the estimate from the probability sample and the complementary portion to the non-probability sample. So if alpha is between 0 and 1, this is basically, maybe it's 60% and 40%. How would you assign that alpha? Well, there's numerous ways of doing that. Popular way to be estimate the variances from the 2 samples and then assign alpha as the ratio of the variance of sample B over the sum of the variances. Another approach that might be reasonable would be to assign alpha in proportion to the effective sample sizes. So give a little more weight to the sample that has more cases, or you could do effective sample sizes to kind of downweight the nominal sample sizes if there are underlying design effects or extra variable weights coming out of the calibration procedure, et cetera. Okay, so once we have that alpha composite factor, we can actually build that into a single set of weights if we want. So we could have a single data set that has cases from both samples, and we would just take the probability weight and multiply that by alpha if it's a case from sample A, or the calibrated weight for the non-probability sample multiplied by 1 minus alpha. When it comes to, so having this data set structured in this way is just convenient because then you can do one pass through your data set and get an estimated total. When it comes to estimating a variance for that combined data set or this combined estimator that's pooling from the two samples, we still do need to estimate the variances separately. Okay, so we would estimate them and put them together using the formula at the bottom of this slide. So those are just a few examples of our particular problem. Again, I recommend, if you're not familiar with it, to check out the non-prob SVY package. It does have a lot of tools that are, with just a few commands, can generate some of these weights to enable you to combine a non-probability and probability sample. In terms of areas of further research for our study, one thing we could consider is Bayesian approaches. We were focused at this first iteration on solutions that would have available off-the-shelf software packages that could be, used by a variety of statisticians with a variety of backgrounds, but there are Bayesian approaches out there. Some other considerations are thinking about alternative starting values for the non-probability sampling weight. So in our scenario, we had an implied starting value of 1.0. You see that in some other similar scenarios in other studies, but it's possible, depending on how the non-probability sample data was generated anyways, that we could potentially start with something other than 1.0 and get slightly different properties of those weights for the non-probability sample. Another thing that's particularly interesting here is we're generally assuming that the two samples are independent. That's what those combined variance formula is doing. But there could be a scenario, particularly if you have clustering in an in-person health survey that's being done across the country, where that wouldn't be the case, that you could have data collection occurring, within the same clusters or clusters within strata. So rethinking how the variance would be estimated if your two samples were not independent, as it's often assumed, would be a worthwhile area for further research, and perhaps the first place to look for coming up with a reasonable variance estimate would be a replication-based approach. So that marks the end of our talk, and I thank you all for tuning in. We'll stop sharing.
Thanks, Taylor. Just saw a question pop up on the Q&A if you want to see it.
Question is, could the non-probability sample be an entire administrative data set? Is there any reason is there holes in the administrative data set that you would be maybe doing the probability sample to fill in? Or could it be that maybe you had a probability sample that you wanted to use totals from the administrative data set to serve as like benchmark figures so that you can create some calibrated weights to hit that? I think my answer would be it is probably possible. It would depend on the context. So when I think of an administrative data set, unless there are like known deficiencies with it or gaps, often we would use that as a source for benchmark totals. But if there's a scenario where that administrative data set had some unequal rates of missingness, and then a probability sample was deemed to look a little better and more representative, I think you could fit within this model, treating that administrative data set as the non-probability sample.
Yeah, Taylor, what about, I think, the situation where like you measure something maybe on some of the things are on the survey but not on the administrative data, so you might want to.
Well, that's true. So that would be in another scenario where you have like Y's and X's only on the
Just wrong thing.
survey, and then the administrative data set just has. Am I getting twisted up here?
Yeah, one of them. It's late today.
Yeah. Um, I don't know. Am I getting twisted around here, Matt? What would be that? I mean, usually it's that the non-probability sample has the X's and the Y's, and the probability
Oh yeah,
sample
you're
has
right.
the Y's. So
Yeah, maybe it's just a coverage issue or something. Yeah.
yeah. And by the way, there are functions and tools within the non-prob SVY package to handle other scenarios like that one. Our particular scenario we were looking at was constrained by what I would call kind of a convenient constraint that we have both the X's and the Y's and both the prob and non-prob sample, but there are tools within that package to deal with that other situation where the survey has the X's and the Y's, but the non-prob, or the survey only has the X's, but the non-prob data set has the X's and the Y's.
Well, we did amazing on time, so we can pat ourselves on the back. We've got another minute or two, but then I think we might be ready to close it out. And yep, we've got all the contact information for the speakers. So if you have any follow-up, feel free to reach out to anyone individually. Should I turn it back to you, Lisa, Peter?
Sure, we have very short announcements at the end of the day. People are probably going to be sick and tired of hearing from me. Anyway, and I'll share my screen. Hopefully I won't overshare my screen as I've been doing every now and then. Thank you so much, Matt, for organizing this session. It was really interesting. I found each of the talks really compelling, and they really fit together quite well. So greatly appreciate the effort that you put in to organize this panel. It was really I really appreciated it.